Right, guys. The last taught section from me is the kinetic theory of gases. So you're going to make notes along the way. Pause whenever you need. It's on page 136 and 137. But I've got a lot of additional points that will help explain the gaps that your book misses. So there's no real case where a gas behaves as a perfect ideal gas. So those are in a real life, there's no perfect situation. So close to an ideal gas. So when gases get very, very high temperature, we're assuming there's no forces between the particles. I'll look at that in a little bit more detail later on when we look at the assumption. And a low pressure when the volume is considered as zero. Okay, so at low pressure, we can consider the volume of each particle as being as a zero because it's not moving very fast at low pressure. The particles are not moving very fast. So those are the assumptions that we can make. And the behavior of the gases in these two conditions is quite close to an ideal gas. Helium as an element, small particles, and there's no real forces between the particles. This isn't a gas. It's quite close to an ideal gas behavior. Okay. Now, the next part, the beginning of this lesson, we are going to look at gases moving within a simple situation in a box. Okay. So what we are looking at is a gas moving, let's say it's a cube, and the distance x, y, and z are exactly the same. We're looking at the Cartesian coordinates x, y, and z, and we are looking at the pressure created by a gas on a single wall of that box. Okay, now, so the pressure created by the force needed to make the particle change direction. Okay, so Newton's third law is what we're going to start off with. So if this particle moves in the x direction, so we're going to move the particle back and forward, so left and right, hitting the wall, bouncing back, hitting the other wall, and continuously bouncing back left and right. Now, when the particle strikes the wall, it will create a force on the wall due to the change of its momentum. Okay, and due to Newton's third law, that the force the particle creates on the wall is equal to the force on the particle in the opposite direction. Okay, and the opposite direction is put there with that negative sign. Newton's second law. So what's the force that is created on the particle by the wall? So the force on the particle is the change in momentum of the particle over the time between successive collisions. And I'm going to look at that separately. So first, let's look at the change in momentum. So I'm going to look at these pictures underneath to help me. We're going to look at one of this is the first assumption that we're going to look at from the ideal gas property. So assuming collisions are elastic, that means that after the collision, after this particle moves, hits this wall and bounces back off into this direction, it holds the same speed. So if the speed incoming is Cx, so we're using this notation, it'll become apparent why I'm using this. C is a speed, x is the direction in which it's moving, and it's moving to the left, hits that wall, elastic collision, bounces off the other direction, but because it's moving in the opposite direction, I'm going to include the negative sign because it's a vector. So when the particle's moving to the right, it's got a minus sign. So elastic collision, left hits the wall on the left and then moves to the right. Okay, now I'm only considering the collision against the wall on the left. All of the walls we look at later on. Now, mass times by the speed is the momentum, and the change in momentum is the final momentum, which is minus mass times by the speed in the x direction, minus the initial momentum, which is mass times the speed in the x direction. And we get the change in momentum as being minus 2 times mass times by speed in the x direction. Now, the time it takes between, remember we said that this is where we introduce all three more assumptions. So the first assumption is assuming the size of the particle is much smaller than the size of the box. So this is tiny compared to the size of the box. Let's look at the extreme case where this particle is more or less the same size as the box. Okay, so in that situation, what we've got is not much movement of the particle hitting that wall, assuming that the time of the impact is much less than the time between the impact. Now, what I mean by time between the impact is the time it takes for the particle to hit the wall, bounce off, hit the other wall, and then come back. Okay, so the time between the impact is the time taken for the particle to hit the wall and come back to hit the same wall again. Okay, now, so assuming the time of impact, the time the particle is in contact with the wall is much, much less than the time it takes between the collision, between the successive collision. Now, one of the reasons why we make this assumption, this was the hardest part for me to get my head around, to be honest, and it's still somewhat like that. So because we say that the particle is tiny, the particle doesn't deform upon impact. So upon it hits, it's not really deforming. If it's not deforming, then the time of impact is 0. Okay, so if the time of impact is 0 and the wall itself doesn't deform either, then what we've got here from the change of momentum over time is that's an infinite force. That does not make any sense for an infinite force to be created at that point. But because we've made the assumption that the particle is tiny, then the frequency of collision, time between successive collisions, will give rise to pressure. So the more frequent the particles collide, the greater the pressure. That concept it makes more sense. So that's where I think the assumption falls in. Assuming there are no forces between the particles, so when the particles, which would slow them down between collisions. So imagine this particle hits the wall, bounces off, hits another particle, slows down, and then comes back to hit that wall and back to hit the original wall. That timing goes off. So we're saying that, assuming there are no forces between particle, so we take care of that as well. So in essence, we have got a wall. If this is a distance x, that's a distance z, and that's the distance y. If it's a cube, it'll be LLL. The time between the impact on the left wall of the particle is the distance divided by the speed. So we are only considering this wall and the particle moving in the x direction, we are looking at the time of impact between successive collisions on that same wall, not this wall. We're not looking at this wall here. So the particle hits this wall, bounces off, hits this wall, comes back to hit this wall. So the distance covered is 2 times by x, and we know that the speed doesn't change, so that's the speed in the x direction. And that will give us the time between successive collisions on that same wall. Now, the force on the particle, we had this expression above as well, is the change in momentum. We've already discussed that, is minus 2 times the mass times the speed in the x direction. And then the time between the collision is 2 times the distance divided by the speed. And algebraically just manipulating that, that ends up being minus times by the mass times by minus mcx squared over x. Okay, now that is the force on the particle by the wall. Now, considering Newton's third law, we said that the force on the particle is the same as the force on the wall, but in the opposite direction. That's where the negative sign drops out. So the force on the wall is equal to the mass of the particle times by the speed of the particle in the x direction squared over the distance or the size or the horizontal distance of that box. The force created by one particle, so this is the force created by one particle hitting the box on just one face. Okay, so the pressure is known as the force over the area. So that's there. We've just created an expression. So the force on the wall is this, divided by the area that it hits, and we'll just go back up. The area is y times by z. Okay, and just doing algebraic manipulation, we get mass times by the speed squared in the x direction divided by x, y, z, x times y times z, which is the volume of the container. And if I just rearrange that, so the pressure times by the volume is equal to the mass of the particle times by the speed squared. So what we are looking at, we're just looking at one particle in the x direction. If there are n particles, so now we are looking at many particles in the box, but we're considering the direction to remain in the x. We'll use y, z later on. So if there's n particles in the box, all moving in the x direction, then the total pressure in the volume that we have got, the volume not going to change, but the pressure will, is, this is, let's say, one particle. So that's the expression of one particle. So I'm going to label that with a 1. Let's say another particle, that's going to have the same expression. You got another particle and another particle and so on and so on. Okay, so this is the pressure due to many particles in a given volume. I could have had volume underneath as a division sign here and left it, so I would have had many particles